Hey there, and welcome. Today, we're cracking a secret code that's hiding in plain sight, right at the very heart of trigonometry. It's a set of rules so powerful, they can take a totally confusing equation and make it simple, even elegant. So, get ready, because we're about to dive into the Pythagorean identities. All right, here's our game plan. We're going to start with something we all know, triangles, and see how they magically lead us to circles. Then we'll forge what I like to call a master key identity. After that, we'll use that key to unlock two more identities, and finally, we'll put them to work and solve a really tricky problem. By the end, you'll have a complete new toolkit.
So first up, from triangles to circles. We're about to build a bridge from a super old theorem you definitely learned in school to the very core of modern trig.
And that really brings us to the big question here, doesn't it? What in the world does a rule for flat, pointy triangles have to do with the smooth, rolling waves of sine and cosine? You know, it feels like they come from two totally different universes, but as you're about to see, they are deeply, deeply connected.
It all kicks off with our old friend Pythagoras' theorem. You probably remember it as a squared plus b squared equals c squared. For hundreds of years, that was the absolute law for right-angled triangles. But its true power, its hidden potential, gets unlocked when we take it out of the world of triangles and drop it into a circle. And that's the secret ingredient.
Okay, so let's go ahead and forge that master key. We're going to see exactly how that simple rule for triangles helps us build our very first and honestly most important trigonometric identity. Seriously, this is where the magic happens. The bridge connecting geometry to trigonometry is something called the unit circle. All it is a circle with a radius of 1. And its equation? It's just x squared plus y squared equals 1. Now, wait a second. Take a look at that. Does it ring a bell? It should. It looks a lot like Pythagoras' theorem, and that is absolutely not a coincidence. Okay, so how do we make the jump? It's actually way simpler than you might think. On this special circle, any point's x-coordinate is just the cosine of the angle theta, and the y-coordinate is the sine of that angle. So all we do is take our circle equation from step 1, and we substitute those trig values right in. That gives us cosine theta squared plus sine theta squared equals 1. We just flip it around to the standard way of writing it, and boom, there it is. And this right here, this is the big one. Sine squared theta plus cosine squared theta equals 1. This is what we're calling the master key, and for good reason. If you can remember just this one identity, you basically have the keys to the whole kingdom.
And here's the best part, you don't need to cram 3 different complicated-looking formulas into your brain. All you need is that one master key and, well, a tiny bit of algebra. We're about to just remix it to find everything else we need.
Okay, check out the first remix. We start with our master key. Then, we do something that might seem a bit random at first. We divide every single piece of it by cosine squared theta. Well, we know that sine over cosine is tangent, so sine squared over cosine squared is tangent squared. Cosine squared divided by itself is just 1. And 1 over cosine squared, well, that's the definition of secant squared. And would you look at that? Just like magic, we've got our second identity. So, what happens if we run that same play again, but with a slight twist? We go back to our trusted master key, but this time, let's divide everything by sine squared theta. Okay, sine squared over itself is 1. Cosine squared over sine squared, that's cotangent squared. And 1 over sine squared is cosecant squared. And there it is. That's our third and final identity. See? No extra memorization needed. Okay, cool. So we've got these 3 rules, but what are they actually good for? Let's see them in action, because that's where you'll understand their real power. We're going to solve an equation that, at first glance, looks like a total nightmare. Here's our problem, pulled right from the Math Center's source material. Solve 2 sine squared x plus cosine x equals 1. I mean, how are you even supposed to approach that? The big problem is that it's mixing 2 different trig functions. You're juggling sines and cosines in the same equation. It's a mess. Well, this is exactly where our cheat code comes into play. We look at that equation and we spot a sine squared x. And because we have our master key identity, we know we can swap that out for 1 minus cosine squared x. This single move is the key that's going to untangle this whole thing. So let's just walk through it. First, we make the substitution. Then we expand the brackets and just tidy up a little. We move everything over to one side, and look what we have. It's just a standard quadratic equation. But instead of the variable being x, our variable is cosine x. No big deal. We can factor it just like any other quadratic.
And that breaks our really complex problem down into two super simple equations to solve. We literally just turned that messy trig equation into a basic algebra problem you've probably solved 100 times.
So let's wrap this all up by putting all our discoveries together. What we've really done today is build a seriously powerful new toolkit for all your trigonometry adventures.
And here it is, your own personal trig cheat sheet. First, you have the master key. This one, you gotta memorize it. Put it on a sticky note. But the other two, the tangent, secant, and the cotangent, cosecant identities, you now know the trick to derive them anytime you need them. These three rules are going to be your best friends.
And why does any of this matter outside of a math class? Well, because these identities are absolutely fundamental. They're used to simplify really complex problems in any field where waves and angles are critical. I mean, we're talking about everything from calculating orbits in astronomy and plotting a course in navigation to designing complex structures in engineering and circuits in electronics.
So we'll leave you with this thought. We just saw how one of these simple rules transformed a messy equation into something we could actually solve. They bring order to chaos. So the real question is, now that you have the keys, what other complex problems are just out there waiting for you to unlock them?